All right, so let's take a look. We're going to look at Chapter 2, the molecular nature of matter and change. Components of matter is Chapter 2. A little bit of a breakdown. We'll go through elements, compounds, and mixtures. We're going to talk briefly about 2.2, 2.3, 2.4, and 2.5. They're not going to be anything we spend a lot of time on. Mention them, kind of go over them, and move forward. All right, and then 2.6, 2.7, 2.8, and 2.9 I want to spend more time on. All right, here we go. Okay, I don't really like the way this slide is set up. In my brain, when I look at things, I see elements are the opposite of compounds. Elements are the exact same type of what we call an atom. An atom is the smallest something can be actually broken down into and retain its properties. So an element, we like gold, hydrogen, copper, plutonium. Those would be elements. They only consist of one type of atom. The atom is the same one over and over again. So a block of gold consists of billions upon billions upon billions of gold atoms. Right? Now, the other one is called a compound, which we'll do on the next page. But you can look at the figure in A, figure 2.1, and see that they're all they're singular, but they can be more than one. They're all the exact same type. In B, we have more than one type, right? So that's really a molecule. And actually, that's also an element. So these two examples on this page are both elements. One is an atom, an A, and one is a molecule. A molecule for us right now, and this will change as we move forward, is a grouping of one or more different types of elements. Keep going with the stuff. This is a compound. This is the actual opposite of an element. A compound is two or more elements combined. And you can see by the picture 2.1c, you can see that you have 3 blue spheres and 1 brownish sphere. Each of them are exactly the same. They're what we call pure substances. Elements and compounds we call pure substances. The opposite of a pure substance is a mixture. So we look at D, they've taken all 3 of those things and mixed them together. And it's 2 different things. It's either 2 different elements with a compound or 2 different compounds. Any way they throw them together, they're mixed together. That's hence the name mixture. And so when you look at the picture in D, you can see that the pink spheres are individual elements that are atoms. The yellow spheres are molecules that are elements. And then the light blue and the brown sphere together is a compound. All of those are pure substances, but when they get mixed together, they're called a mixture. And they're not combined with each other chemically. So you can separate them. That's what we call a physical property. All right, and here are some properties of sodium chlorine and sodium chloride. And they give them to you so you can see what they kind of look like or how they behave when they're individual. And then they have them again when they're combined. So we look at the bottom picture. Sodium is a soft metal. It should be gray. Chlorine is a brown gas. When we mix them together, we get something that is a white solid crystal. Okay? And the behavior, the properties change. You can see the melting points, the boiling points, the color, the density, all that shifts when we chemically combine them. All right, we'll do this one relatively quick. It's a picture, so it's nice. Some of these we'll do together right now. Another time we'll wait and we'll do them together in class. All right, the following scenes represent an atomic scale view of 3 samples of matter. Describe each sample as an element, compound, or mixture. All right, let's start with A. A is pretty simple to see. You have elements, you have compounds, you have different kinds of elements all together. Okay, so that would be a mixture. B, they're all singular, but they're all the same. So they're atoms for sure, and they're elements. And C, you can see there are blue spheres and a big black sphere, right? So that one would be a combination together chemically of 2 elements, which makes it a compound. So we have 2 different compounds. Sorry, we have the same compound inside there, but 2 different elements make up the compound. And now we kind of get into the law of conservation of mass, which says that the total mass of a reaction should not change. The mass of the reactant should be equal to the mass of the products. They should be consistent when you run the reaction. The total amount never changes. Even if you burn something, what happens is some of the gases escape. And that's where we actually have it drop in weight, but we're not controlling the air that's actually being produced or put into it. All right, that's basically a restatement. We can see the bottom two numbers. When we react with calcium oxide with carbon dioxide, we produce calcium carbonate. And so our mass should be conserved. So 56.08 should be added to 44, should give us 100.08. It doesn't always work out perfectly like that, but it should. If everything went exactly what it's supposed to, and we controlled them like we should, that should hold. That law always is true, but sometimes we miss things as we're going and collecting our samples. Constant composition tells me that the percentages stay the same. This is calcium carbonate, and they give you the percentages: 40% by mass calcium, 12% carbon, 48% oxygen, which means anytime I come across calcium carbonate, that should be the percentages of how it breaks down every single time. That's why we call it definite or constant every single time. Okay, and they do a little bit of analysis here. No matter how much they break it down, they always end up with the same basic numbers. It's always the same percentage. We're going to hold off on sample 2. We're going to do it together. Multiple proportions, the big thing about that is elements combine in small whole number ratios. So it's possible to have multiple proportions. Like in this example, I have carbon monoxide and carbon dioxide. Carbon monoxide, it's the single oxygen, single red sphere with the black sphere to the right. That's the combination that goes between. That's the percentage next to it. And it always ends up in whole number ratios, so there's 1 to 1. Carbon dioxide, right, ends up with a 1 to 2, but they always should end up in whole number ratios. And this is just them proving it and showing you what happens so they can come up with it. This should be quick. Dalton's atomic theory. It's on there so you can see it. The big thing when you look at this, that if you read through it, you can see that it says atoms cannot be created or destroyed. Law of conservation of matter. We can't break them apart, though, either. It should be somewhere in there as well, which we know is not quite true. We can break atoms into smaller substances. We call them subatomic, smaller than atoms. Atoms can be converted between elements of another element by ordinary chemical means. That should be true as well. And number 3, this is wrong, but close enough. They're not all identical in mass. There's different parts between them because when we have something called an isotope, which has different numbers of neutrons, okay? And when we combine atoms, they tend to end up in specific or whole number ratios of different elements. That's true. It explains the mass laws here, right? Can't be created or destroyed, converted into other types of atoms. Everything has a fixed mass. Don't change these things, right? Compound specific ratios. Good stuff. All right. It's a picture, so we can do the picture together. The following scene represents the atomic scale view of a chemical reaction. Which of the mass laws? Mass conservation, definite composition, or multiple portions is illustrated. Well, let's see. If we have the same number of purple spheres on both sides and the same number of green spheres on both sides, then we should have the law of mass conservation. Law of conservation of mass. Now, let's say it. So I feel like we do. There are 1, 2, 3, 4, 5, 6 purple spheres on one side, 7 purple spheres on one side, and 7 on the other side. So we conserved mass. We definitely did that. Definite composition. Once they form on the other side, we can see that the molecule is consistent. It has 2 green spheres and 1 purple sphere. And then multiple portions, I don't think that one's being shown. There's only one combination that is happening between the green and the blue. So I don't think the last one is shown. History, we'll go through this relatively quick. This is not something stressed on the AP Chem exam. This is a cathode ray tube. And essentially what happened with the cathode ray tube is there was a beam of light, or a beam of electrons actually, that actually flow through the cathode ray tube. And when they held a magnet up close to it, it bent the beam. It told them that there were particles in it that were charged, opposite in charge, whatever side of the magnet it was on. And that's what it shows on side there, right? The beam bends, depending on the magnet. Millikan's oil drop experiment. This is relatively quick too. This established a mass-charge ratio. What they would do is suspend oil droplets inside a magnetic field. They could adjust the actual magnetic field to the point where the magnets would not fall any farther. That gave them a charge-to-mass ratio. And that's what he's explaining here. Rutherford. Now, this is an interesting guy. He was what they call an experimental physicist. He's not one of those guys that sat around and came up with theories. He's all about testing things. So typically what happens when you have somebody that's an experimental scientist, they're also inventors. They figure out ways to actually make things. So if they don't have it and they need something, then they have to invent it or find somebody else's and curve it that way. Here's the big thing for Rutherford. He shot a beam of alpha particles at a piece of gold foil. Most of them went straight on through, which told him that most of the atom was made of empty space. Occasionally, these alpha particles would shoot backwards at him. And alpha particles have a positive charge. So what happens is when it comes in contact with something positive, it should repel. And so that's what happened. The positive alpha particles came in contact with something solid that was positive inside the gold sheet. Only some of the time, though. Most of the time, they shot right on through. So again, that reinforced, like I've already said, that most of the atom is made of empty space. But occasionally, it ran into something positive, the same as the alpha particle, and dense. And we call that the nucleus. Okay, and this is the general breakdown of the atom. The accepted value tends to be, the accepted model now, it tends to be that we have a nucleus that's compact, it's positively charged because it's filled with protons, and a neutral substance called a neutron, and they're about the same weight. Neutrons are a little bit larger, a little bit more massive, and then we're surrounded by this electron cloud of electrons, which basically means they're moving at super high speeds around a very small space. They appear to be everywhere in a given moment in time. And there they are. We can see the masses and the charges. Protons and neutrons are exactly opposite in charge. Shows that on there. Their sizes, protons and neutrons, pretty close. Electrons are about, I don't know, what's that, about 10,000 times smaller? I think if I do my math right, relatively quick. And it tells you where they're located, which you should already know. This is called a nuclear symbol. The X represents the atomic symbol on the periodic table. The Z represents the atomic number. To me, they're kind of redundant. You don't need to write both of those. So typically, I don't write the atomic number on the nuclear symbol. The top number represents the mass of the atom. All the mass of the atom is located in the nucleus. And there are two things inside the nucleus. The positively charged nucleus. A proton, which is positive, and neutrons. So if I know the atomic number, then I know the mass number, then I know the number of neutrons. Isotopes are different kinds of, or different forms of the same atom, different masses. So typically they have these two right here. They have 235-92 uranium and 238-92. You notice the 92 doesn't change because that's the number of protons. That tells me it's uranium. It tells me the identity. But the top number does, the mass changes. So what happens is some atoms of uranium are more massive than other atoms of uranium. They have different numbers of neutrons, and they exist in different amounts. All right, this is talking about neutrons and stuff like that, electrons, which we'll walk through together. We'll do on when? We'll do the next time we meet. Oh, skipped over some stuff. Right? Sorry. All right, so basically what we're looking at here is high source of energy electrons. They shoot through. It bounces off things, right? I told them the outside basically has lots of electrons on the outside. This is important. This is a mass spec. This helps us determine the number of isotopes and the percentage they actually exist in. And again, we'll spend more time on this together in class. It's easier to do it that way. But this is a readout of the mass spec, which we'll go into more detail next time when I see you. Again, we'll do this too as well. Beautiful modern periodic table. Atomic number, that's consistent. Atomic symbol is consistent. The atomic mass, sometimes they call it the atomic weight. Atomic mass is more accurate. Is basically the weighted average of all the given isotopes of an element, which we'll walk you through when I do those two examples. The weighted average, that's the average number. The 9.012 for beryllium is the average of all the isotopes of beryllium. And here's some examples. Again, we'll do 2.6 when we meet together. Okay, so this is the formation of an ionic compound. So let's talk about an ionic compound, because it's probably been at least a few months to a year for the last time most of you have seen it, probably longer for a lot of you. Ionic compound basically means you have two elements that kind of work opposite of one another. One likes to lose electrons. We call those metals. And one likes to gain electrons. We call them nonmetals. So when I do something simple as sodium, which is the example they used earlier, they have sodium metal and chlorine gas, and they put them together, and they show you kind of examples of how this works. So sodium is a solid, so it should be nice and organized, repeating pattern over and over and over again. It's a metal, so it's a sea of electrons, which we'll talk about later. And then you have the nonmetal, which is the chlorine gas, and they're held together by covalent bonds. And they're sharing electrons. They like to do that. When we put the two of them together, there's an exchange of electrons. You can see the yellow in over here in between. It's exchange. So the sodium loses an electron because it's a metal, and metals are losers. That's important, right? You should have got that out of general count. Metals are losers. And then the other one over here, the green one, it's going to gain the electrons. And it gains it because nonmetals are the opposite of metals. They didn't even get creative with the names here. They called one metal and one, well, it's not a metal, so we'll call it a nonmetal. Well, the metal's a loser. That's what makes it a metal. So what makes something a not metal or a non-metal is that it gains electrons. And that's what's occurring here. And we go to the actual example. Now they're attracted to each other because, well, it lost an electron, so it's positive. It gained an electron, so it's negative. And we know opposites attract, so it creates this thing over here. It's called a crystal lattice. And that's what sodium chloride looks like, hexagonal. Okay? This is something called Coulomb's law, which we'll keep talking about over and over and over again. But basically what it tells you is the smaller the atoms are, the closer they can get together. So the stronger their attractive forces. That's what the first column says, to the left. Second one says the larger they are in charge, the larger they are in size, the more attractive they are to each other. Let's try that again, right? The first column says that they're both +1, -1, so the size matters more than anything else. When you go from the first column to the second column, the charge goes up, so they're more attracted to each other. So I would say that the 2+ and 2- in the upper right-hand corner should be the ones that are most attracted to each other. Coulomb's law basically says the larger the charge, the smaller the atom, the more they're attracted to each other. And we have our periodic table, and we're showing the elements between the, we have the noble gas in between, the positive and negatives, how they're attracted to each other. And the noble gas is closest. And we'll come back to these as well, right? A covalent bond is when the atoms share electrons. It becomes more stable. There's a magic number in chemistry, we'll call it 8, right? 8 electrons is what most things want. I believe these are hydrogen because there's only one proton in there. And hydrogen gets stable with 2 electrons. It has something to do with the size of its orbital that it's in. That's okay. And what they're looking to do is share those electrons so that they all can get to a magic number. Well, the magic number, if we go back a slide, is almost always based, or 2 slides, it's almost always based on the noble gas. So the noble gas are desirable. They're stable. They don't react with anything because they have a stable configuration of electrons. Their outer electrons are filled. So for most elements, that should be 8 electrons. But for small ones like hydrogen and helium, they only need 2. We'll explain that when we get there. Not in this chapter, I don't believe, right? And now I guess we're going to change our molecule definition. A molecule is basically 2 atoms held together by covalent bonds. They share electrons, okay? And an ion is 2 or more atoms together as well, but they're not sharing electrons. An ionic bond is when you have, we showed with the sodium chloride, where one likes to lose electrons. We call that a metal, a loser, and one likes to gain one, which is not a metal, which is called a non-metal. And so what happens is the electrons exchange, right? There are no molecules in ionic compounds. We actually give them a different name. We call them formula units because really all they are is repeating patterns. Right? And then we have some elements that normally exist together, right? They're molecules. Elements that are molecules, and here they are. The ones in light green are what we call diatomic. The other ones we won't really use as much. But the diatomic will come into more play when we do the gas laws. Oh, these are polyatomic ions. So the beginning part here, polyatomic ions tend to be in ionic compounds. And we can look at the polyatomic ion carbonate on the right-hand side. And it consists of 2 red spheres and 1 gray sphere. The 2 red spheres are oxygen, and the gray sphere is going to be carbon, and they're actually sharing electrons. So the ion itself is sharing electrons, but there's too many electrons in it, so it has a -2 charge overall. It's called the polyatomic ion. So the ion's held together, the polyatomic ion is held together by covalent bonds, but overall it's an ionic compound. Okay, chemical formulas, right? You know what they are. They tell us the element and how many of each element's inside of it. Right? They don't give a ton of information, but they do that for us. All right, so now we're going to do some what we call nomenclature. Nomenclature. And we're going to deal with binary ionic compounds. I believe that we'll just do the binary for all these. Some simple concepts that come through here. There's always a cation, which we write first, which is positive. And plus the cat, there's a cat in there with a T, right? And then the anion, which is negative. It's always written second. So, for example, sodium chloride. Sodium is positive because it's a metal, it loses electrons, and the chlorine is negative. It's an anion, right? So it's written second. Okay, we always change the ending if they're just elements involved here. We always make the ending IDE. Okay, we name the cation just like it was supposed to be, right? We don't do anything crazy to it. So when we put calcium and bromine together, we call it calcium bromide, right? The ending to the second one. If it's an element, regardless if it's ionic or molecular, the ending is always going to be IDE. Okay, and so here are some common monatomic ions. It's easier to show this in a periodic table. It's much easier to show it on there. Okay, so let's go to the periodic table and show you why. In chemistry, the magic number is 8. So all the elements go to 8. So we start in column 1. They have 1 valence electron. 1A. And then we go to 2A. 2A has 2 valence electrons. So since metals are losers, they lose their outer electrons, or their valence electrons. So group 1A loses electrons, so they're all positive 1. That's what they are. That's how they're consistent. They always are. They always do that. Group 2A likes to lose 2 electrons, so they're plus 2. Right? We'll skip the middle. Right? We'll come back to them, see what's going on over there. And we'll go to column 3A or 13, and those end up being plus 3 most times because they have 3 valence electrons. Now, are we figuring out a pattern here? Ready? Let's watch. Ready? Column 1A was 1 valence electron. Column 2A was 2 valence electrons. Column 3A is 3 valence electrons. Column 4 would be 4 electrons. Now, we only show the tin and the lead on the bottom. We don't show the other ones because, well, these behave kind of funny. We don't like to worry about this column as much. So carbon doesn't do well in ionic compounds. We're not going to worry about that one. We'll talk about it, but they tend not to form ionic, just individual carbons. And then we'll do 5A, right? It has 5 valence electrons. And so in this one, nonmetals are gainers, right? And we said the magic number was 8. So nitrogen likes to gain 3 electrons to get to 8 valence electrons. So therefore, it's a -3 charge. Oxygen has 6 valence electrons. It likes to gain 2 more to get to 8, so it's a -2 charge. And then the last column, right, fluorine, chlorine, bromine, and iodine all like to go ahead and gain 1 electron, become like the since they have 7 already, they like to gain 1. And we put hydrogen on both sides. It's a strange one, right? Because they can do both. Most of the time we deal with it in acid, then it ends up being positive. But it could be both, depending where it's written. If we see hydrogen written first in the compound, it's the cation. If we see it written second in the compound, it's the anion, and we name them accordingly. Okay? You name the following from each of the pairs, right? We'll do it relatively simple. Or actually, we'll wait, right? We'll wait. And we'll wait on this one as well, because it gets a little bit trickier. Right, so these are the elements in the center. They go ahead and lose electrons too because they're all metals, and they can have more than 1 charge. Because of the way that their electron configuration is set up, they are capable of making more than 1 charge. So this is a list of pretty common polyatomic ions. And if you notice the name, systematic name there, right? Systematic name, not the common name. That's an old system. Don't use it anymore. But the systematic name tells us that I write the Roman numeral next to it to tell you the charge on the metal ion. And I only do it for ones that can have more than one charge. I wouldn't do it for group 1 or group 2 on the periodic table. I do it for the ones in the center and the ones that can have more than 1 charge. And the bigger the atom, more capable it is. Again, we'll wait, come back to it, okay? And these are a list of some common polyatomic ions. I'll give you a more extensive list so that I can kind of push you a little bit with problems, but these are the ones that are going to be used most of the time. Other ones I give you probably won't do much. Right? We only have one positive one typically. Hydronium, it doesn't really form compounds all that well. We would never use it in a polyatomic. They're listed here. It's important we do acids and bases, but it's not important to us overall. Okay? And then when we name these oxo anions, right? When we use the negative ones on here, like they've done, we'll go ahead and add some roots. So I'll explain this as well in my classes. Okay, and so now we're bouncing over to the covalent or molecular compounds. We can call them molecular because that's what they really are anyways. They always use prefixes to tell you how many of each are there. That's what they do. Okay, so you need to have these written down or memorized and whatever works for you. Right? Again, we'll wait on this one. We'll wait on this one. Okay, and then we'll do acids. These are the rules. Okay, make sure you know them. We'll do them in class together. Again, same kind of thing. These are the, I don't know why that one's out of place. I have to check that to make sure as we move forward. But binary, covalent are molecules. We only worry about binary, which is 2 elements for this one. For the ionic, it was 2 ions, a positive, negative. But for covalent or molecular compound, I like molecular better. For molecular compounds, it's always going to be just 2 nonmetals. Always going to be 2, right? And so we always do 2 things, right? You're going to go ahead and one with the lower group numbers written first. Okay, the lower group numbers written first. But we tend to go ahead and be the more electronegative, but we're not worried about that. All right, and the ending to the second one, just like in the ionic, if it's an element written second, which it will be for covalent, we make the ending IDE. Okay, and again, we'll do these later in class. Okay, and we're not doing these at all. I got to get rid of them. But they're neat, right? Okay, molecular masses, okay, from chemical formulas. So I know this is a little bit of a throwback. We haven't seen it in a while, but it should be relatively easy. If we use our periodic table, we can figure out the atomic mass of hydrogen, which is 1.008 AMU. There are 2 hydrogen atoms in water. We take that number, 2, we multiply 1 by the atomic mass, and that gives us the amount of mass of hydrogen in a water molecule. And then we do the same thing for the oxygen. There's only 1 atom here. It's 16 AMU. We end up with 16 and 2, we get 18 atomic mass units. Atomic mass unit is a very small thing. We're talking about only 1 molecule. That's why we're using it. And we're going to shift it later on, but for now, to figure out the molecular mass, you just add up the number of atoms multiplied by their atomic mass. And we'll do that later. And this one later as well. And now we're writing formula, different ways to show the molecule. The most useful is obviously going to be when they start going and showing you how they're together. The molecular formula of water just shows you how many you have of each, but the other 4 show you how they're kind of, the hydrogen's not really attached to other hydrogen. They're both attached to the oxygen. Okay? More pictures. We're not going to do a ton of this stuff, heterogeneous mixtures. Hetero means different. Homo means the same. A homogeneous mixture is called a solution. They're more workable. You make things a solution and then they have predictable properties. If we use water, which we will most of the time in the solution, we call it aqueous. So homogeneous mixture is a solution. It's really how we get most ionic compounds to react. We dump in water, we dissolve them, and we get a reaction. All reactions are based on movement. Okay? And the distinction between mixtures and compounds is mixtures have different things inside of them. You can separate it by ordinary physical means. Compounds are chemically bonded to each other. It's a chemical bond between them. So a compound would have either a covalent bond inside of it or an ionic bond inside of it. And the mixture would just have attractive forces inside of it. And so this is kind of different, right? So let's do this relatively quick. For some reason, the AP thinks the separation techniques, which we use typically to separate heterogeneous or homogeneous mixtures, are based on a couple different things. Filtration is simple. It's like a coffee filter, right? These are the same thing. You take solids that are inside a liquid, you pour the mixture through one of the filters, you catch the solid inside of it, right? We use filters all the time, right? Crystallization, it's a little bit different, a little bit trickier. We won't do it for a while. In some situations, you can go ahead and make some ions come out of solution by dumping small amounts of a negative ion in with it. It crystallizes on the bottom. We'll talk about that. Distillation is based on boiling point. Okay? You might have heard the term still when we refer to things like people making moonshine. In that scenario, what happens is they have water and an alcohol mix. What they do is they boil the solution at 80 degrees, which water doesn't boil at, but alcohol does. And the alcohol boils out and they collect it in a cool container, right? And so they end up separating the water and the alcohol from each other, because when we do that, distillation, it's based on boiling points. If we heat it at 80 degrees, water will not boil, but the alcohol will, and we can use it to separate the two. Okay? And then chromatography is the other one we'll look at. It's based on what it is, polar or non-polar. This is kind of an important one that got asked on the AP exam 2 years ago. And it's based on polarity. And the concept is like dissolves like, or like likes itself, right? So if they're positive, then they like each other. If they're negative, they like each other. Or if they're polar molecules, they like each other. And polar means like little magnets, and non-polar means not like little magnets, right? We have our basic setup for distillation. You can see that we are boiling the water on the one hand, on the left-hand side. It's going through a cool tube. And on the other side, right, we have just whatever is left over. So it's a separation based on boiling points. Okay? This is chromatography. It's not paper chromatography. It's still based on the whole positive negative. And what they do is they pack tubes full of different kind of substances. Those substances are either polar or non-polar, and the actual thing goes through quicker if it matches up with what we call the solvent. Okay, and gas chromatography works the same way. We can actually use this, take the data, and use it to actually figure out what's inside the solution.